Hello and welcome back to the course. My name is Mohammad Razaghi. I'm a researcher at EPFL, and in this session, I would like to share our approach towards transition to smart cities with you. My core argument in this session is that in socio-technical systems, which cities are of course great examples of such systems, we are dealing with complexity. And that to manage and govern the transition process in such complex contexts, three key considerations are vital. First, to have a holistic approach. Second, to have a long-term perspective. And third, to be flexible in managing the process of transition. Let me start with the notion of complexity in socio-technical systems and what does that mean? As you know, feedback loops are essential elements when we are talking about systems. In socio-technical systems, the feedback loops are present at the technical, the social, and what we call the socio-technical levels. In the technical level, we have feedback loops both inside and across different subsystems. Let's, for example, think of the transportation or the energy systems. As an example of feedback loops inside these technical systems, you can, for example, imagine how changes in the routing or the routes of the bus system will have impact on the demand for the metro or the light rail system in the city. As an example of feedback loops across different technical systems, you can think of, for example, the impact of introducing electric buses in the transportation network and the effects that it would have on the demand for electricity and the energy infrastructure in the city. Feedback loops also exist in the social level, as we call that. For example, between the economic and the social subsystems, between the economic and the political subsystems, and so on and so forth. You can think of that between the economy and environment and so on. But also, the feedback loops exist in the overall socio-technical system, and this is what is really important for us when talking about transition towards the smart cities. For example, let me give you an example of a new subsidy scheme on public transportation tariffs. This new tariff system can be seen as an economic decision, but introducing this change can have very profound impacts on all the other subsystems as well, such as putting more pressure on the transportation infrastructure due to the increasing demand for public transportation services by the citizens. Now the service is cheaper, so the demand might go higher. Also, the availability of more affordable public transportation in the city might affect the citizens' choice of place for living. For example, you can imagine that those groups in the city that are less advantaged compared to the other ones might decide to move to the outskirts of the city where the housing is more affordable, while they can still commute to the city center and access to their jobs thanks to the availability of this cheap public transportation tariff scheme that is already introduced in the system. This can have significant impacts on the social dimensions of life in the city as well. For example, you can imagine how it can result in deeper social segregation between different neighborhoods in the city, because not anymore all the groups of the citizens are living in one place. Some are living in one neighborhood, the other ones are living in other neighborhoods, which are more advantaged probably. Or even on the political dimensions of governance and management of city. For example, you can imagine how this new tariff system can help the current administration to win the next election probably, because this new tariff system would be very visible to the eyes of the citizens who are benefiting from that tariff. This simple example already shows the three important characteristics in socio-technical systems which result in complexity, namely the interdependency, which means that a change or the ultimate performance of one subsystem in the broader socio-technical system will have impacts on the performance of other subsystems as well. And ultimately, this is the combination of the performance of all these subsystems which result in the performance of the overall system, and not each of them in isolation. The second important point here is the path dependency, which means that every change or decision in a socio-technical system is dependent on the changes that occurred in the system in the previous stages, which often take quite some time until their effects become fully utilized in the system and are observable and become tangible for the citizens and the decision makers, of course. And last but not least, we are talking about irreversibility. Irreversibility means that we cannot just undo the impacts of the decisions that we make and the changes that we introduce in socio-technical systems, because the impacts of a change in one subsystem is affecting many other subsystems as well, and often over a very long period of time, which makes it almost impossible to redo the effects that one change or one decision has in the socio-technical system. Let us now discuss what are the implications of these important features of socio-technical systems for management and governance of the transition towards smart cities. The interdependency among different subsystems of a socio-technical system call for adopting a holistic and quite often multidisciplinary approach when managing the transition process towards smart cities. Indeed, because introducing changes in one infrastructure will influence on and will be influenced by changes in other subsystems of our broader socio-technical system, we have to have a holistic approach in managing the different elements of the transition process towards smart cities. By adopting a holistic approach, I mean that we have to consider technological, economic, social, political, institutional, and also, very importantly, environmental considerations in a holistic fashion and not just in isolation from each other when we are trying to manage the process of transition towards smart cities. Without such a holistic approach, new initiatives in complex socio-technical systems like smart cities often fail or even result in adverse effects that we don't even foresee them in advance and will distort the performance of the system potentially. The path dependency of changes in socio-technical systems calls for adopting a long-term perspective in management and governance of transition towards smart cities. Let me benefit from the S-curve of innovation to elaborate on this point. The S-curve of innovation, which is the result of a lot of empirical research, shows us that the performance or progress of introducing an innovation, which can be technical or institutional, is dependent on time. But the relationship between the time and the progress of an innovation is not a linear relationship. Indeed, as you can see in this graph, innovations often take quite some significant time to be developed until they reach to a point where we can see a rapid progress in terms of their performance gains. This is this rapid growth that you can see in the graph. And after this rapid growth phase, innovations often enter a period of relatively stable progress when their performance does not significantly change over time anymore. This means that when a new innovation, being technological or institutional, is introduced in a city, to help the city move towards becoming more smart, a relatively long period of time will be required until the expected performance from this innovation can be utilized. And an important point here is that the different innovations have their own different S-curves as well. For example, the technological innovations, you can look at the red curve, for example, in this graph, often reach to their maximum progress in a shorter period of time when you compare it with social or institutional innovations, which you can think of them as the yellow or the green curves here. But as we discussed before, transition in socio-technical systems is not the result of changes in one single subsystem, but is indeed the result of a series of changes in these interdependent subsystems of the broader socio-technical system. So we need even longer times until all the introduced changes in the system reach to their expected performance level. the technological innovations, the social innovations, the financial innovations, and so on and so forth. And this implies that without a long-term perspective, introducing new initiatives in the city often result in failure. The irreversibility of changes in the socio-technical systems is one of the main reasons we need to adopt a flexible approach in management and governance of transition towards smart cities. Innovations such as the ones that we have already discussed in the smart energy and smart transportation blocks can introduce significant changes in established infrastructure systems, and hopefully they can also improve the performance of the systems. But unfortunately, innovations often fail, and the rate of failure among innovations in socio-technical systems is even higher, something around 90%. As you can see in this simplified diagram, only few innovations would eventually become part of the existing socio-technical systems, while most of the others fail in different stages of their life cycle. This can be seen, for example, in the case of different innovations to realize the idea of driverless vehicles, or the different renewable energy technologies, where only one or very few of the existing technologies will ultimately become the dominant technology in this sector. And this is indeed the battle that different companies are trying to win at this stage of transition towards the smart cities. Because most of the innovations are doomed to failure, unfortunately, and because our decisions and changes in socio-technical systems are not easily reversible, it is very important that we try to keep all the options that are available as long as possible that we can, and to avoid becoming locked in premature technologies that might prove to be failures in a few years. This is even more important when we consider that not all the innovations can affect an infrastructure are necessarily generated in the same sector. Like, think of what happened in the battery technology, which started in the energy sector, but now has disruptive impacts on the transportation infrastructure thanks to the introduction of the electric vehicles. Now, let me conclude this session by using a simple diagram, which I call a transition triangle. As we discussed in this session, it is very important to adopt a holistic approach in management and governance of transition towards smart cities, considering technological, economic, social, political, and environmental dimensions of any change that is going to be introduced in the city towards becoming more smart. We also have to have a long-term perspective in managing the transition towards smart cities, because we are dealing with different kinds of past dependencies in the system, what we already see in the S-curve of innovation. And last but not least, we have to keep as much flexibility as possible when managing a transition process towards the smart cities, to effectively deal with the irreversible nature of the changes that are introduced in socio-technical systems. But following these guidelines is easier said than done in practice. For example, it looks quite paradoxical, at the first glance at least, to have a long-term perspective while staying flexible in the same time. And this is why in the next sessions of this MOOC, we try to get into more details on how we can manage and govern the process of transition towards the smart cities understood as complex socio-technical systems. So stay tuned.